Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Fundamentals of Multiferroism from the paper Functional Materials. So students, let us see what are we going to study in this module. First, we will be discussing about the fundamentals of multiferroicity. Second, we will discuss the classification of materials. Third, we will discuss the various examples of materials and their characteristics. Lastly, we will also discuss about the application potential. So let us start with a brief introduction about this module. A ferroic material is defined as a material which is exhibiting at least two of the ferroelectric or ferromagnetic or ferroelastic ordering in the single phase state. These ordering are typically manifested in the presence of a well-defined hysteresis loop when the material is switched under the bipolar electric field, magnetic field, or mechanical stress. More recently, ferroelectric ordering, another ordering mechanism, has been proposed. On the other hand, magnetoelectric coupling in the materials is a general phenomena which could be present whether or not the material exhibits the magnetic or electrical ordering. For example, it could occur in the paraelectric, ferromagnetic materials, or it can be mediated by other parameters such as strain. Hence, the term multiferroic would mean a material exhibiting two or more of the above ordering mechanisms. More recently, multiferroic materials, they have raised tremendous research interests because of their potential for several exciting device applications. Examples includes the multi-state memory element or sensors or spintronic devices. However, there are several challenges as there are not many naturally occurring materials which shows multiferroism, and hence most are artificially prepared in the laboratories. In addition, most of the materials shows transition temperature which are below the room temperature, making these devices operation impractical. Also, there could be issues with respect to their fabricability in pure phase form. However, despite these challenges, researchers' quest remains to develop such materials simply because they offer exciting opportunities from both the fundamental and application perspectives. So we are going to study some of the basic aspects of multiferroic materials and the attributes of a few example materials. Let us start with the characteristics of a ferroelectric material. The figure shows the ideal PE hysteresis loop for a ferroelectric material, where the saturation polarization, that is, plus PS, corresponds to the state when all the spins are aligned parallel to each other, and minus PS corresponds to the anti-parallel spins. The structure shows a typical AbO3 perovskite unit cell, which is a well-known ferroelectric material. So now we will study about the ferroelectrics. Let's discuss about the four properties of ferroelectric materials, and then we will study their applications. First, they are non-centrosymmetric. Second, reversal of polarization and deformation by varying the electric field and stress. Third, they exhibit the spontaneous polarization in the absence of electric field. Fourth, they also follows the Curie-Weiss behavior. Now their applications. They can be used as sensors, actuators and transducers, capacitors because they have high K dielectrics. They can be used in memories, for example, non-volatile memories, in the case of field effect transistors, or they can be used in microwave applications. Ferromagnetism, the spontaneous magnetization in the absence of magnetic field, is referred as the ferromagnetism. Now, as we can see from this B versus H curve, which shows that the saturation B, that is the saturation magnetization Bs, corresponds to the alignment of magnetic spins parallel to each other, whereas minus Bs, which are in the opposite direction. The ferromagnetism is used in transformer cores, permanent magnets, electromagnets. The Stoner's band theory explains the ferromagnetism, which describes there are three types of exchange interaction. First is the exchange interaction. Second, exchange energy, which is basically the driving force. Third is the exchange effect, which dominates over the band energy only in the narrow bands. Example, those arising from d electrons. Other magnetic orderings. Now students, let us discuss about the other magnetic orderings leading to antiferromagnetism and ferromagnetism effects. First, we will discuss about the antiferromagnetism. Here, there is no net magnetization due to anti-parallel alignment of magnetic dipoles, which is shown in the figure also. The examples of antiferromagnetic materials are chromium, manganese, manganese oxide, manganese sulfide, and iron oxide. Next is ferrimagnetism, where there is the anti-parallel alignment with unequal dipole moment. This leads to some remnant magnetization. The example of ferrimagnetism are ferrites. Now let us discuss about the two major effects, that is multiferroism and magnetoelectric effect. The combination of electricity and magnetism is not a recent topic, rather it was visualized as early as in 19th century through famous Maxwell's equations. However, in most cases, electrical and magnetic ordering in solids are considered to be independent of each other. This is mainly because of the fact that electrical properties are due to electric charges of electrons and ions are, whilst magnetic properties of a material are governed by the electron spins. Recent years have seen cases where the two degrees of freedom couple quite strongly, as in the case of spintronics. In spintronics, one can make devices where transport current can be manipulated by controlling the spins of electrons and vice versa. As Comiskey notes that although evidence of a strong coupling between electrical and magnetic degrees of freedom in insulating solids dates back to the work of Pierre Curie, it was a short remark by Landau and Lifshitz in 1959 which marks the beginning. Let us point out two more phenomena which in principle could exist. One is piezomagnetism, which consists of linear coupling between a magnetic field in a solid and a deformation analogous to piezoelectricity. The other is a linear coupling between magnetic and electric fields in a media, which would cause, for example, a magnetization proportional to an electric field. Both these phenomena could exist for certain classes of magnetocrystalline symmetry. We will not, however, discuss these phenomena in more detail because it seems that till present, presumably, they have not been observed in any substance. This was then followed by the discovery of magnetoelectric effect and the concept of multiferroics. So, a multiferroic material is basically a material which exhibits two or more functional ordering, example, ferroelectric or ferromagnetic or ferroelastic ordering, a feature typically demonstrated by the presence of a well-defined hysteresis loop when the material switched electrically, magnetically, or mechanically. Next is the magnetoelectric effect. Magnetoelectric coupling in the materials, on the other hand, is a more general phenomenon irrespective of the state of magnetic and electrical ordering. For example, it could occur in paraelectric ferromagnetic materials, or it can be mediated by other parameters such as strain. Multiferroics. The simultaneous existence of ferroelectricity and the magnetism in a single phase, that is, spontaneous magnetization, spontaneous polarization, spontaneous deformation, possibility of conducting the polarization by changing the magnetic field and vice versa. Also, they have additional degree of freedom in device fabrication. There are very few materials which exhibit this effect in a single phase form. Now they have variety of applications. First, sensors and actuators with additional degree of freedom in operation. Second, multi-state memory devices. Third, electrically controlled magnetic resonance devices. Fourth, transducers with magnetically modulated piezoelectricity. Fifth, spintronic devices. The classification of multiferroic materials and magnetoelectric materials. The figure explains the various possible scenarios. While there are a large number of magnetically and electrically polarizable materials, there are only a few materials which show ferroelectric and ferromagnetic ordering. Magnetoelectric materials are those materials that are simultaneously electrically and magnetically polarizable, while multiferroic materials are strictly those type of materials which exhibit simultaneous presence of ferroelectric and ferromagnetic ordering. While strictly speaking, multiferroism means only for those materials in which there is coupling of more than one order parameter. Nowadays, researchers have also started including antiferromagnetism as well as ferrimagnetism also with multiferroic materials. Many of the multiferroic materials are either rare earth magnetite such as TBMnO3, TBMn2O5, HOMn2O5 or ferrites such as BiFeO3 or LuFe2O4 or transition metal perovskite oxides, example BiMnO3 and YMnO3. A few non-oxide materials can also be multiferroics, examples being spinel chalcogenides, example zinc chromium selenide and barium nickel ferrite. Given that the multiferroic materials show more than one ferroic ordering, the envisaged applications are numerous. Some of these applications can be future memory devices with multiple degree of control, sensors and actuators that be controlled by more than one type of stimuli, spintronic devices where spin of electron can be controlled electrically. Now students, let us discuss about the historical perspective of magnetoelectric effect. Magnetoelectric effect was first observed by Rontgen in 1888 and by Pierre Curie in 1894 in two independent studies. Rontgen found that a dielectric, when moved in an electric field, became magnetized, and conversely, it became polarized when moved in a magnetic field. In contrast, Curie pointed out the relation between the magnetoelectric effect as the crystal symmetry. It was Debye who first coined the term magnetoelectric in 1926. First material with magnetoelectric switching was chromium oxide with small magnitudes of induced polarization and magnetization. Subsequently, the research was carried on various materials, and it is now established that more than 80 compounds showed magnetoelectric effect, which include gallium ferrite, a few borosides, and few phosphates. Nickel iodine boroside Ni3b7O13I is the first multiferroic material that was discovered in 1966 by Ascher et al. And shows simultaneous presence of ferroelectricity and weak ferromagnetism at 64 Kelvin. Subsequently, several studies were made on various boroside compounds. However, most of them had quite complex crystal structures, and materials were not very useful from technological viewpoint due to their low transition temperatures. This was followed by studies on various mixed perovskites, primarily as solid solutions of two perovskite structured oxides. Russian scientists took lead in these investigations, where they replaced some of the D0 type cations in the ferroelectric perovskite oxides with magnetic Dn type elements in order to induce magnetic ordering. One of first such compounds was a solid solution of lead-based compounds. PbFe2/3, W1/3O3 and PbMg1/2, W1/2O3. In this solid solution, ferroelectricity is originated by diamagnetic magnesium and tungsten atoms, while magnetic ordering is caused by Fe3 plus ions. A few other candidates which showed ferroelectricity and antiferromagnetic ordering were iron or cobalt doped lead tungstates or lead tantallates. However, most of these materials had either very low Curie temperatures or Néel temperature, which prevented further research on these. Subsequently, the research focus was on other perovskite materials, which are either manganites or ferrites and have been more promising than previously researched materials, which will be discussed later. Now let us discuss about the requirements for a material to be ferromagnetic, ferroelectric, and finally the multiferroic. For a ferromagnetic material, the d electrons are needed, that is iron, manganese and nickel, and La and strontium MnO3 also exhibits the ferromagnetism. For a ferroelectric material, the d electrons are not needed, that is the barium titanate is the best example. Then the question arises, how can a material exhibits both the effects? So students, now we will discuss about the requirements for a material to be multiferroic. There are many material requirements which need to be fulfilled for a material to be called as multiferroic. For instance, for ferroelectricity, as we have already discussed, it must be non-centrosymmetric, to possess the electrical polarization, and there are 31 point groups which allows this. Out of these, 13 point groups allows the occurrence of both the properties simultaneously. These point groups may lead to large number of possible materials exhibiting multiferroism, so it is quite unlikely that symmetry plays an important role in determining whether a material will be multiferroic or not. There are contradictions in terms of the requirement of functionality. Electrically speaking, one requires a ferroelectric material to be the insulator, while it is not a constraint for a ferromagnetic material. For the most ferromagnets, high electrical conductivity is due to higher number of free charge carriers, whereas reverse is true for ferroelectrics and insulators which require to be insulating. However, a few magnetic oxides, example half metallic magnets and ferrimagnetic oxides, exhibit reasonable spontaneous magnetism whilst simultaneously being semiconducting or insulating. As far as chemistry of the material is concerned, most ferroelectrics require ions whose shells are filled. If the material has perovskite structure, then the B atom at the center of BO6 octahedra must have filled D shells, that is, has D0 type electronic configuration. In contrast, magnetic materials require d orbitals to be partially occupied for possessing magnetic ordering. Latter also imposes constraints to maintaining the center of symmetry in these systems. Another factor that could be analyzed is the size of small cation, especially in the perspective of perovskites. However, upon comparison, one finds that this is not a valid argument as sizes vary considerably for kinds of compounds. Another contrast between ferroelectric and ferromagnetically ordered system is that the wave structure is distorted, while ferroelectrics undergo a phase transition as the temperature changes. Low temperature phase being non-centrosymmetric, ferromagnetic materials show significant John-Taylor distortion arising from partially filled D shells. Latter is almost absent in most ferroelectrics, as it has been postulated that John-Taylor distorted structure may have less driving force for off-center displacement of B ions in the octahedra. Another condition which ferroelectric materials show is that they possess a time reversal symmetry but do not exhibit a space inversion symmetry. On the other hand, ferromagnetic materials possess the space inversion symmetry but do not exhibit the time inversion symmetry. So now to conclude that there is no constraint on various material parameters which prevent the materials from being multiferroic, that is, simultaneously ferroelectric and ferromagnetic. A multiferroic does not possess either of time reversal and space inversion symmetry. Magnetoelectric coupling. According to Landau theory, the magnetoelectric effect in a single phase material can be described through the expansion of the free energy as F as a function of E and H is equal to F naught minus Pi S multiplied by EI minus Mi S multiplied by Hi minus half of epsilon naught epsilon Ij Ei Ej minus half mu naught mu Ij Hi Hj minus alpha Ij Ei Hj plus beta Ijk by 2 multiplied by Ei Hj Hk plus gamma Ijk by 2 Hi Ej Ek plus so on, where Ei is the ith component of E and Hi is the ith component of H are the electric and magnetic fields, while epsilon and mu are the dielectric and magnetic susceptibilities respectively. The second and the third term in these equations denotes the temperature dependent electrical polarization corresponding to Ei and Pis and magnetization corresponds to Hi and Mis respectively. Fourth and the fifth terms describes the effect of electrical and magnetic field on materials, electrical and magnetic behavior respectively. Here, epsilon Ij and mu Ij are second rank tensor quantities and is usually independent of Ei or Hi in the materials without the corresponding ferroic ordering. The sixth term, consisting of alpha Ij, describes the linear magnetoelectric coupling and is typically of interest. And the next two terms, which consist of beta Ijk and gamma Ijk, are the third rank tensors and represents higher order magnetoelectric coupling coefficients. Now, one can determine the magnetoelectric effects by calculating Pi as a function of Hj and Mi as a function of Ej, which can be obtained by differentiating the previous equation with respect to Ei and Hi respectively, and then making Ei and Hi equating to 0. This yields Pi is equal to minus del F by del I, which is equal to Pi S plus epsilon naught epsilon Ij Ej plus alpha Ij Hj plus beta Ijk by 2 Hj Hk plus so on, and Mi is equal to minus del F by del Hi, which is equal to Mi S plus mu naught mu Ij Hj plus alpha Ij Ei plus beta Ijk Ei Hj plus so on. In most cases, we are interested in the linear magnetoelectric coefficient, that is alpha Ij, because magnetoelectric effect is of linear nature in most compounds. This coefficient allows one to quantify the dependence of polarization or magnetization on magnetic field or electric field. In the case of multiferroics, having both ferroelectric and ferromagnetic ordering, large linear magnetoelectric effects are usually expected because such materials often possess large dielectric susceptibility and magnetic permeability respectively. The limit of linear magnetoelectric coefficient is expressed as alpha square ij is less than or equal to epsilon naught mu naught epsilon ij mu ij. So students, let us summarize what we have learned in this module. First, the multiferroic materials, which are modern materials where one absorbs the coupling of functional order parameter in a single phase. Second, magnetoelectric materials are those materials that are simultaneously electrically and magnetically polarizable and are not necessarily multiferroic. Third, magnetoelectric coupling is quantified by the linear magnetoelectric coefficient. As the magnetoelectric effect, it is linear in the most of the compounds. Thank you.